All right, my friends, let's take a look at motion with constant acceleration. Constant acceleration means the acceleration doesn't change as time goes by, so a graph of the acceleration will just be a horizontal line. And constant acceleration also means that acceleration as a function of time is, well, just a constant that we're going to call a. Well, if you have an acceleration against time graph, the area under that graph represents the change in velocity that will happen over a given time interval. Well, so what happens is after a certain time interval passes, maybe you started at a particular initial velocity, but after that time interval passes, your velocity will change by this amount at, which was the area under the acceleration time graph. And so your velocity function is going to look like this. A straight line, if you had a constant acceleration, you're going to have a velocity time graph that's linear, in fact, with a slope equal to a. So where we end up at the end of the time interval, we're going to call that the final velocity. Well, so to see what that final velocity is, we just need to see how far did we move vertically on this graph. And what you can see is, well, how far up are we vertically? Well, we're up v initial plus at. And so this is one of the what's called kinematic equations for constant acceleration. That's in the yellow box here. Well, we can play the same game going from the velocity graph to the position graph. As it turns out, the area under a velocity time curve tells you your change in position. Well, so let's look at the area under this thing. Well, we see a rectangle here and a triangle. Well, so let's look at the area under the rectangle. The length times width. So where the base of this rectangle is t units long and it's v initial tall. So the area is just v initial times t. But we also have this triangle here. And of course, triangles are 1/2 the base times the height. So 1/2 of, well, I'm going to use the base as this side, so it is of length t. And then the height of this triangle is at, so you have 1/2 TAT, otherwise known as 1/2 AT squared. Well, so what you do with that grand total area is that is how far you'll move after a time interval has passed. Well, so we start at position x initial, and at the end of the time interval, we're going to have to tack on top of that a certain distance, and that is going to be this total area that was under the velocity time graph. And so we tack on v initial t plus 1/2 at squared, and so get to the final position. And so this is our final position, xf. So we'll move in a curvy way because our speed is changing if we're accelerating. So our position time graph will be curved. And this final position you can find by looking at how far up we are vertically on this graph. Well, we're going to be x initial plus v initial t plus 1/2 at squared. And so this is a second one of these equations for constant acceleration motion. Now, a way that I tend to use this a lot, and many of your physics teachers will, is if you move the x initial to the left-hand side, so you'd have like x final minus x initial. That's really just the change in position, delta x. So that's just moving this initial position to the left side. And you can see that's equal to v naught t plus 1/2 at squared. So these are two equations that you get to use when the acceleration is constant. Turns out from these two you can derive a third. Well, so here are those two equations. And what we're going to do is we're going to try to eliminate t as a variable, because there may be a situation where you just don't happen to know how many seconds long some interval is. And so what we're going to do is we're going to solve the left-hand equation, the simpler one, for t. So manipulating that, you'd get t is v final minus v initial divided by a. That would be isolating t. And then what we're going to do is just substitute that t into the right-hand equation here. And what that's going to do is eliminate t as a variable. So we'll get a relationship that's valid that doesn't involve t. Well, so when you do that, straight just plugging this expression in for the t, well, you'd have v naught t. So we basically just need to multiply this expression by v naught. And so you'd have v naught vf minus v naught squared over a. And then likewise putting this thing in and squaring it, you would get this expression. Notice that I only have one power of a in the denominator here because Squaring this would give me an a squared in the denominator, but I also have an a that would be upstairs that would cancel it, and so then you're just going to get something that looks like this. Well, now we're just going to manipulate this around to simplify it a bit. What I'm going to do first is multiply both sides of this equation by a. So that would remove the a from the denominators over here. And then also I expanded this expression out on the right using the FOIL method. Okay, so you can go back to your Algebra 1 or Algebra 2 and just FOIL this VF minus V naught quantity squared, and you'll get these terms here. And then finally, what I'm going to do is multiply both sides of this equation by 2 to kind of get rid of these 1/2s that you see here. So I'm just multiplying both sides by 2. Well, now if you look at what happens, we have a term that has 2v naught vf, and then we have a term that's minus 2v naught vf. So that's going to cancel out. We won't have to worry about that term. And then you also notice that we have a term that goes like minus 2v initial squared, but then plus v initial squared. So that's going to conspire to make a minus v initial squared. Well, so what you end up finding out then is the right-hand side here is really just v final squared minus v initial squared. And then the other side of the equation is 2a delta x. Well, so what you have is this third, what's called kinematic equation for constant acceleration. That's really nothing new in that it just comes from the first two. You can, in fact, of the 3 equations in the solid boxes here, you can derive any one from the other 2. So the thing to remember is these equations are only valid when the acceleration is constant. So to hit this idea a little bit more, so here are these 3 so-called kinematic equations, again, used for constant acceleration. Don't use them if the acceleration is time dependent. So to show you exactly what I mean, let's look at an example of when you shouldn't use those equations. So here would be such an example. It says, and if an object starts from rest at the position x equals 0 and accelerates such that a of t is 2t squared, find how far it travels in 2 seconds. Now, a kid who's going to screw this up, what they'll do is they'll read that this says find how far, and they'll go, oh, how far, and they'll go for a relationship like this that has delta x, change in position, which would tell me how far. But again, this equation for delta x that's up at the top here, it is only valid for constant acceleration. It will let you down if you try to use it. You'll get the wrong answer. So what you have to do instead is actually use calculus in this case. So what we have here is an acceleration function 2t squared. What we need to do is find a velocity function such that if we took the slope of the velocity function, we would get this acceleration. Well, so the way this works is you need a function such that if you do what's called taking its derivative or taking its slope, you'll get this acceleration function 2t squared. Now, how does this work? When you take a slope or take the derivative of a polynomial, you bring the exponent down and reduce it by 1. That's called taking the derivative. Well, so let's check that that would work, this process of bringing the exponent down and reducing it by 1. If I bring this exponent down in front, I would get 3 times 2/3, which would give me 2. That would give me this coefficient 2. And then reducing the exponent 3 to a 2, it would indeed give me 2t squared. So this process of reducing the exponent is called taking a derivative. That would take you from velocity to acceleration. Going the reverse direction is called taking the antiderivative, and you pump the exponent up. Okay, so you'd have v of t is 2/3 t cubed plus v initial. The v initial in my little example here happens to be 0 since it starts from rest. So the velocity function would actually look like this, 2/3 t cubed, right? So we have to do this again to get to the position function. What we need to do is find a position function such that when I bring the exponent down and reduce it by 1, I would get this 2/3 t cubed. And so as it turns out, that function would look like this. Well, let's check this. If I bring the exponent down in front, I would get 4 times 4/6, or 4 times 1/6, which would be 4/6, otherwise known as 2/3. So that would work. And then the 4 would be reduced to a 3. So this function, x of t is 1/6 t to the 4th plus x initial, would be a reasonable position function appropriate for this case. x initial happens to be 0 in the little prompt that I gave, so the time-dependent position function would look like this: 1/6 t to the fourth. And then to figure out how far it moved, I would plug in 2 for t. So I would get 1/6 of 2 to the fourth, otherwise known as 16/6, which is the same as 2.67 meters. So here we had to use, a little bit some more advanced math. We had to use some a little bit of calculus. The key point here being, do not try to use this constant acceleration equation because the acceleration just flat wasn't constant. Um, so thanks for checking this out. Little key thing to think about with these, if you remember, any one of these equations can be derived from the other two. So sometimes when you're working these problems with your friends, you will notice that you may choose a different pathway than your friends, but you can still get the right answer. What you'll find is either a student might be able to pick one equation and do it in one step, or somebody else might use two of the equations together. And that's because these three things aren't really independent of each other. You can derive any one from the other two. So hopefully that helps. Again, use these only when the acceleration is constant. And thank you for watching. I hope you found this helpful.